We always hear about these super fancy, complex AI algorithms, right? But what's the real secret ingredient that makes them smart? Well, today, we're pulling back the curtain on the unsung hero of machine learning, feature engineering. Okay, let's really think about this for a second. You can have the most amazing, world-class recipe, but if your ingredients are, garbage, your dish is going to be a disaster. It's the exact same thing in machine learning. The algorithm is the recipe, but the data, the features, those are the ingredients. And trust me, the quality of those ingredients is everything. So, what is feature engineering? Simply put, it's the essential prep work. It's this whole process of selecting, cleaning, and transforming that raw, messy data into a clean, structured format that a model can actually understand and learn from. Without this step, even the smartest algorithm on the planet is basically just flying blind. So, how do we actually do it? Well, we're going to follow a data scientist's roadmap. First, we'll tackle those annoying missing pieces in our data. Then, we'll become translators for all the non-numeric info. After that, we'll make sure everything is playing on the same scale, and finally, we'll do the final edit and pick out only the most important features for our model. Sound good? Let's jump in. All right, our very first challenge is probably the most common one you'll ever face with real-world data: missing values. It's like trying to build a puzzle, but a bunch of the pieces are just gone. You're not going to get a very clear picture, and neither will your model. So you open up your data set and it's just riddled with these blank spaces, often shown as NaN, which just means not a number. Could be a sensor failed, maybe someone just skipped a question on a form, who knows? But whatever the reason, we absolutely cannot just ignore them. If we do, our AI's predictions will be all over the place. So what's the game plan? We've got two main strategies. The first one is pretty blunt: elimination. You just delete any row or column that has a missing value. It's fast, sure, but you risk throwing away a ton of really valuable information. The other approach, which is often better, is called imputation. That's where we intelligently fill in the blanks, usually with something like the average value for that whole column. This way, we get to keep all of our precious data. Okay, next up, we need to put on our translator hats. You see, machine learning models at their core, they speak one language, and one language only: numbers. But a whole lot of our data comes in as words or categories. Things like red, green, or blue. We've got to translate that for a model. Now, it turns out not all categories are created equal. Some of them, which we call ordinal features, have a natural built-in order. Think about t-shirt sizes. It's obvious to everyone that large is bigger than small. But then you have others, called nominal features, that have no order whatsoever. I mean, is red greater than blue? The question doesn't even make sense, right? And this is a huge, massive trap. If we just blindly assign numbers to our nominal features, like, let's say red equals 1 and green equals 2, our model is going to make a totally wrong assumption. It's going to think that green is somehow more or better than red. This creates a fake relationship that will completely confuse your model and give you terrible results. So how do we solve this puzzle? With a really clever trick called one-hot encoding. Instead of jamming everything into one column, we create a brand new column for every single category. Then we just use simple ones and zeros to show if that category is there or not. Let me show you what I mean. Okay, so here's our simple wine dataset before we touch it. We've got one column for color with the words red and white. A machine learning model looks at this and has absolutely no idea what to do with it. And voila, look at the result. The original color column, it's gone. And in its place, we have two new columns: color_red and color_white. So for a red wine, color_red gets a 1 and color white gets a 0. It's that simple. Now the model understands the category perfectly without assuming any fake order. Problem solved. Our next job is to be the great equalizer. Imagine one feature in your data ranges from 0 to 1, but another one goes from 0 all the way up to 1,000. Well, the model's naturally going to think the second one is 1,000 times more important. Even if it's not, we have to fix that imbalance. Taking another look at our wine data, you can see this problem in action. The alcohol content is hanging out around 13, but then this other chemical, proline, has a value of 746. An algorithm would be completely dominated by that massive proline number and pretty much ignore the others. This is exactly what scaling is meant to prevent. So we've got two main tools for this. First, there's normalization, which basically squishes everything into a nice, tidy range, like 0 to 1. Then there's standardization, which is a bit different. It shifts the data so that the average is 0. It's often the better choice because it handles those really extreme values or outliers much more gracefully. And would you look at that? After we apply normalization, our features are all on a level playing field. That giant proline value isn't overshadowing everything else anymore. Now our model can fairly judge each feature based on how predictive it actually is, not just its random scale. All right, we are at the final stage. We have cleaned, translated, and scaled our data. Now it's time for the final edit, feature selection. Sometimes less really is more, and we need to trim the fat to make our model lean, mean, and powerful. The danger of throwing too many features at a model is a classic problem called overfitting. This is where your model basically just memorizes the training data, noise and all. So it gets a perfect score on the practice test, but then totally bombs the final exam because it can't handle new data it's never seen before. The solution? We reduce the number of features and focus only on the ones that truly matter. One old-school way to do this is called a sequential backward selection. It sounds complicated, but it's really not. You start with all your features. Then you just start taking them away, one by one. And at each step, you remove the feature that hurts your model's performance the least. You just keep doing that until you're left with your chosen number of superstar features. But there's an even more powerful way. We can actually use a model to do the heavy lifting for us. An algorithm like a random forest, which is basically a big team of decision trees all working together, can automatically figure out an importance score for every single feature. It literally tells us which ingredients are having the biggest impact. So, after all that work, what did we find in our wine dataset? Well, using that random forest model, we discovered that these 5 features are the most critical for figuring out the wine type. Proline, the one with that huge scale, is definitely a big deal, along with things like flavonoids, color, and of course, alcohol. We successfully found the signal in all that noise. So let's recap our journey real quick. We cleaned up the missing data. We translated categories into a language the machine could actually speak. We leveled the playing field by equalizing all the scales. And finally, we selected only the most impactful features. 4 crucial steps to turn messy data into machine learning gold. And that is really the big takeaway here. Feature engineering isn't just some boring chore. It's about really understanding your data and carefully crafting it to perfectly solve your problem. Better ingredients, better AI. It really is as simple as that. This whole process, this is the foundation that every single great machine learning model is built on. We've shown you how to clean, shape, and prepare the core ingredients. So the only question left is, what masterpiece are you going to build?